So good morning, everyone. Today I will present you a tutorial on trace-based simulation of MANETs on the example of aeronautical communications. I work University of Technology. This work is done under a national research project called INTERNET, Inter-Aircraft Network, and yeah, it's part of the work of the team in my Institute of Communication Networks. So I will start with the introduction part. One of the newly introduced communication technology for aviation is called the L-band digital aeronautical communication systems, known as LDACs. And this LDACs has two modes of operation, an air-to-ground mode. And an air-to-ground mode in parts where there is a ground station coverage, so in continental area, and there is an air-to-air mode which extends the air-to-ground communication in places where there is no direct ground station coverage. So basically in oceanic areas or in continental areas where there is no ground station in direct communication with the aircraft. And the air-to-air communication involves air traffic control and safety-related communication. So basically, if we look at this figure here, on the left side here, we see USA. On the right side, we see Europe, and the airspace between them in the North Atlantic Ocean is called the North Atlantic Corridor. Basically, it's similar to highway tracks, where the aircraft are separated for safety reasons and for more control of the traffic. What is important here, the requirements in aviation communication is fixed. They are defined, the latency and reliability. And also the message generation is also clearly defined. So when to trigger messages from aircraft, at which conditions. For example, if an aircraft enter an oceanic airspace, it may send a message. For example, if we look at this Gander oceanic airspace, so it may trigger a message when it starts to enter this airspace. For example, also if it change altitude, it needs to communicate this information. So this is the motivation behind our work here on Tracebased, because a lot of things are fixed and defined, and so we can work with traces more than just modeling the behaviors. So as I mentioned to you, the message generation is bound to mobility because it's very connected with events which also have tightly connection with mobility, and which is as well tightly controlled. The mobility is not mobility of aircraft is not something which change through time. Mostly it's fixed through years, going through the same routes and so on. So here, if we go for randomized user behavior, it's not the right model to evaluate this system's key performance indicators, as I mentioned to you. That's why our aim in this work is to show how the OMNeT++ simulator can effectively make use of trace data so that future research with these specific requirements may benefit. Now I will show you the system model. So we have four main components in our tutorial, let us say. So the trace-based mobility, here we depend on already developed OMNeT mobility modules. Trace-based data traffic, here we extend the UDP basic app by including traces as well. Trace-based radio model, which decide whether a packet is successfully received or drop a packet. And finally, an idealized TDMA Medium Access. So I start with the first component, the trace-based mobility. As I mentioned to you, we use already implemented mobility model in OMNeT, the bone motion mobility. The important point here is that aircraft traces are normally given in latitude, altitude, longitude. So we need to convert it to a proper format which is readable by bone motion mobility. This is done by making a conversion through the ECEF coordinates, Earth-centered Earth-fixed coordinates. Then we have Cartesian-like coordinates. So, and this bond motion expect in each line coordinates of an aircraft, XYZ of each aircraft at each specific timestamp. Additionally, also we use the scenario manager, which is also already there in OMNeT, in INET, I would to be more specific. And we use it to create and shut down aircraft in the scenario. So we create them when they enter the simulation area, and we shut down them when they exit the simulation area. The second component is the trace-based data traffic. And as I mentioned to you, it's tightly connected with the mobility model. Repeating what I mentioned already, an aircraft may trigger the generation of a message based on some conditions. For example, entering an oceanic control area, or in a different flight phase where you may change your altitude and so on. That's why data traffic generation is linked to mobility. And for that, we developed a novel UDP trace-based app. It inherits from the UDP basic app. The difference, it requires an additional trace file where you put the triggering time of messages. In UDP basic app, we have a start time, stop time, and send interval. Here we just depend on the trace file and ignore these parameters. And we expect a text file that contain a simulation timestamp in each line. It looks something similar to what you see in this table here, where, for example, you have the triggering time of the first message, second message, and these trace files are generated jointly with the mobility trace file, so outside OMNeT, because it's more convenient. And we give this as inputs to our model to link the mobility to the message generation. And also it's flexible in the sense that it may have different destinations or message sizes. Now we move on to the third component, the idealized TDMA Medium Access. So here there is two questions to answer. The first question, why we go for TDMA-based protocols. The second question, why we go for an idealized version of TDMA. So for the first question, we have, as it's clear, we have large communication ranges, goes up to 370 kilometers. And this prevents us from using CSMA, CA, like medium access control protocols, because from the large communication range, this will result in large delays, which make it almost not possible to operate any kind of CSMA, CA protocols. That's why the actual MAC protocol for LDAX air-to-air will be a TDMA-based protocol. And it's similar to what is already defined for the air-to-ground part, which is also a TDMA-based protocol. Now we go to the second question, why we go for an idealized version in this paper. Routing plays a major role in LDAX air-to-air. As I mentioned to you, LDAX air-to-air extend air-to-ground by the mean of multi-hop communication. So we need routing protocols for this purpose. So the first reason is that before the proposed TDMA-based MAC protocol is sufficiently specified and implemented, we go for an idealized version, which give us a performance not very different from what we expect in TDMA-based protocols. And the second reason, we want to focus on the effects of the routing protocols in isolation of the underlying MAC. So these two together is the reasoning why we go for the idealized TDMA protocol, which doesn't require any kind of, for example, synchronization and so on. We developed a novel TDMA MAC implementation in OMNeT++, which I don't think is available out there yet. And the main thing about how it works, it allocates time slots to users unrealistically through an oracle. So basically, this oracle says whenever a user needs a time slot, it's assigned an exclusive time slot without any control overhead. So we assume there is an entity which knows the information about all nodes and can assign time slots to users without the need of any control overhead. To this point here, we have a global TDMA scheduler entity, and also all the users. So in this case, they are the aircrafts or the ground station. They are equipped with a custom network interface card that provides a TDMA MAC sublayer. So now you have a quick overview about how this idealized TDMA works. I will just go through a flowchart to give you more details about it. So basically, we have the TDMA scheduler, so the entity which knows all the information in a global view. And then each user have a TDMA MAC module in it. So for example, here, user 1 up to user N. And at the initialization phase, all the users will register themselves in the TDMA scheduler. And on the start of the first frame here at this part, the TDMA scheduler will set the schedule for all users. You can see maybe here on the right side, we have the first frame. And as in this case, there is no node want to send any, it doesn't have anything in its buffer. That's why no slot is assigned to any user. We see this X here. And also so the frames is divided. The frame is divided into slots, and here no user need anything, so we don't assign anything. And then whenever any user have something to send in its buffer, it reports the buffer status to the TDMA scheduler. And on the next frame, in the start of the next frame, it sets the schedule for all these users which have something to send. And as we can see also in the right side here, user 1 in this case have some packets in its buffer, and that's why it's assigned slots here. So basically, this is in nutshell how it works. So now we have already discussed the trace-based mobility, trace-based application, and also the idealized TDMA medium access. Now we go for the last part, the radio medium. So this is the last component of our system model. The motivation behind this one, OMNeT already have, I would say, radio models going from the simplest version like unit disk radio up to more complex models which model different behaviors in the net in the channel. But for us, the problem is mainly from the computation complexity of when we go for more realistic channel modeling. As you already can understand, we evaluate the model for hundreds of users, hundreds of aircrafts, and over real world hours. So we go for 1 hour and so on or more. And with all the different other models like the MAC, the complex MAC models or the routing protocols and so on, this leads to a very complex simulation. That's why we go for a simplified and average model to represent the different physical layer aspects, which is important in the air-to-air channel. And for that, we developed a novel trace-based radio model, which extends the unit disk, is a unit disk radio model in the following way. So basically, we have a trace file. This trace file maps a certain signal-to-noise ratio level to a priori computed packet error rate and bit error rate. So then this leads us to this slide. We need first to find out our SNR. Here we did it similarly to what Miguel Belido from German Aerospace Center did. He also a project partner in Internet. So first we obtain the free space pass loss denoted by LP. It has two inputs, the distance and the frequency. The distance between the transmitter and receiver and the transmission frequency. And this is found through equation 1. After you have the pass loss, we calculate the received power. As inputs to the model, you give the transmission power, the transmitter and receiver gains, and the transmitter and receiver losses. So, and this is found through equation 2. After that, we finally found the SNR given the noise figure, the thermal noise density, and the receiver bandwidth through equation 3. So what happens? We have a trace-based receiver module. This extends the unit disk receiver. Unit disk receiver only care about the distance between the transmitter and receiver, but the trace-based receiver do this calculation and find the signal-to-noise ratio, and then pass this signal-to-noise ratio to a novel trace-based error model, which was not before in unit disk radio model. And this trace-based error model uses a trace file I already told you about it. So it's basically a lookup table, and find out which packet error rate and bit error rate maps to this SNR level. What we do is just we round the SNR to the closest matching SNR. Okay, now you know the overview of how this trace-based radio model do. I will show you now an example or a validation scenario to check if this model works. So we did a very simple scenario. We have one transmitter and one receiver. The receiver is located at this location as x equals 0, y equals 0, z equals 30. The transmitter, we choose its location as a variable. So the x axis change from 180 kilometers to up to 1,400 kilometers. And we keep the y-axis and z-axis fixed. And then we check what is the packet error rate level at each of these locations. So these distances are chosen in a way it reflects the entire range of the trace file we have. So going from certain success to certain failure. And next, I will show the results from this scenario. So before the result, we need to look into the trace file. So basically, this trace file is a text file. It has 3 columns. The first column is the SNR level, and second column packet error rate, third column bit error rate. I just organize it here in a table for presentation purpose. As I told you, for example, if you got a signal to noise ratio of 1.2 dB, you round it into 1 dB. Yeah, some also mentioned that we can do, for example, things like care fitting, but for now we just round the SNR value. And yeah, and also if you got any SNR level less than -5 or more than 10, you round it to the closest one. So to -5 and 10 in this case. Here we see the result. In the y-axis, we see the packet error rate. In the x-axis, we see the signal-to-noise ratio in dB. And we can see that the theoretical results and the simulation results are matching with each other. So for example, if we look at SNR level of 8 dB here, we see it gets into 10% packet error rate. And also what we already saw in the trace file, if you got any SNR level larger than 10, we go for the same packet error rate as 10, 10 to the power of -2. And the same goes in the other direction. Okay, now up to this point, we have described all the different models, the different components of our system model. Now we want to combine everything together in this simulation scenario. So this is part of the tutorial. We created a scenario which combine all these different models, trace-based mobility models, the trace-based app, the idealized TDMA, and the trace-based radio model. So basically, this scenario, you have a ground station in the middle, and you have aircrafts which move in a swarm from the west to east. And the communication range of these nodes, aircraft and ground station, is 400 kilometers. So this outer circle we see here. And this ground station has its oceanic control area in a distance of 370.4 kilometers around the ground station. So basically, this gray circle is the oceanic control area. And each aircraft, when it touches this gray circle, it's the first time it sent the entry message, and when it exit this gray circle, it sent the exit message in this case. And also we make the number of aircraft as a variable for this scenario. Here you see the simulation parameters. As I told you, we have the number of aircraft is a variable. We go from 100, 200 up to 500. We use idealized TDMA as our MAC, where the slot duration is 10 milliseconds, and we go for the 10 slots in a frame. We also set the retransmission attempts into 0 to make the results more clear. For the radio model, we use the trace-based radio model with a 400 kilometer communication range. And as I told you, this oceanic airspace is 370.4 kilometers around the ground station. We did the simulation for 10 runs to obtain 95% confidence interval. And the simulation time is chosen to be 10,000 seconds. This is enough to get to this packet error rate level, to have enough packets here. Okay, now we can see the result. It's a very simple result. So in the y-axis, we have the number of packets, and in the x-axis, we have the number of aircrafts. We want to look into the sent packets and the received packets. So as we expect, the sent packets are exactly what we expect in this simulation. So we have each aircraft sent 2 packets, and in total we have 2 times the number of aircrafts. So for example, if we have 100 aircrafts, we have 200 packets sent. So this is somehow validates the UDP Tracebased app, and also validates the TDMA MAC, which shows that it can assign slots for users. And for the received packets, as I told you, in this scenario, we send packets from a distance of 370.4 kilometers when we are this far from the ground station. And this translates here into SNR level of 8 dB. And if we look at the packet error rate, it's 10% in this case. That's why we expect always the number of received packet to be 10% less than the number of sent packets. So for this case, we expect 180 packets received out of 200 packets. So to sum up what I mentioned here as a conclusion, trace-based simulation has been motivated by the evaluation of LDACs air-to-air. As I told you, in aviation communication, we have abundant real-world data available, so we can simulate a communication system under realistic circumstances. Also, a novel data traffic application that links the mobility data and the generation of message is presented. Additionally, an idealized TDMA MAC protocol, which somehow fills a gap in the OMNeT++ toolbox. So it's suitable for simulations where effects of a full-fledged MAC should be suppressed. The implementation of a trace-based radio model for OMNeT++ simulator is done to include realistic radio channel modeling, as I described to you. All these implemented modules are available in GitHub under open licenses in such a way it benefits future research into, it could benefit future research into trace-based scenarios. So, and it's done in a tutorial way, which start from setting the experiment until you plot the results, which is the same as what we saw in this presentation. So for future work, for now, we have the bit error rate in the trace file, but we didn't support it yet in the implementation. So this could be extended to include only the also the bit error rate as a packet error rate. And for now, we don't care about interference between nodes. So everything will be the same, just the difference, we, instead of calculating the SNR, we need to calculate the SINR, the signal to interference and noise ratio. Also, an extension to a radio model that understands multiple orthogonal frequency channels is desirable. So where only nodes with the same frequency can interfere each other. So thank you for listening, and now it's time for questions.
Thank you for your presentation. I have a question about the. You said that collision avoidance is not possible, and is it not possible, or is the reason that it's not as reliable and deterministic that it's not used for that?
It's almost not possible. So for CCMA, CA to work properly, you need somehow negligible propagation delays. So for this distance of 370 kilometers, the propagation delay is 200 milliseconds, which mean you can have a wrong picture about the spectrum on the time you want to send. Yeah. So it will not work with this high propagation delay.
Okay.
My question is about the validation of the models, because as you mentioned, you have certain, let's say, simplifications, but because of preference reasons, so to speak, so you can simulate large networks or a lot of time, but still, what you could do is you in INET, I assume you're using INET, of course. You could also have a more detailed variant of your simulation, which can be used for validate the simplified model, which in turn can be used to simulate your scenarios. But at least you have a more detailed model, which is validating the assumptions that you are doing, especially in the physical layer, for example. But also maybe in the okay, I'm not sure how I would do it exactly, but that's what we often do in wireless networks. So when you have a simplified model, you can validate this against a more detailed, complicated, slower, and more heavyweight model, which you actually don't use to simulate your scenarios, but at least it's more accurate.
Okay.
Especially if you're trying to do this with different, as you mentioned, with in the future, because INET has very detailed models if you want to use those in the physical layer, for example. It's just an idea.
Okay, thanks for the feedback. Yeah, we will consider that in improvements for the tutorial for this model. Yeah. So any other question or feedback?
This just a very general question. This in this ocean control area, these ground stations, are they located off some small islands, or where are these ground stations located?
Yeah, so they should be located in land, in continental area, and also in a place where there is much traffic on it. So not everywhere you have ground stations, mostly in the coast of Europe and USA, and also some part of Iceland and so on. This is if we talk about North Atlantic corridor for this case. But okay. Yeah.
But this 370 kilometers is smaller than the Atlantic corridor, or?
Yeah, because that's why we use multi-hop communication to extend it.
Okay, so you don't have a ground station in this ocean control area, but at the sides, at the borders of it.
So what they do right now? So either they only depend on the communication before they leave the continental area into the oceanic area, and just keep with the regulations, or some aircrafts also are equipped with satellite communication, which is also have very high propagation delay.
Okay.
So this is the motivation of why we do multi-hop communication here.
Okay.
Yeah. Any other question from the audience? Okay, so do we close it here or? we still continue till the end of the